if you did the homework, you just have it out. While I'm taking a peek at that, why don't you think about this, you can call it what you want, sort of warm-up question. It kind of fits into yesterday's lesson, and it kind of fits into today's lesson. It's meant to get you guys to start to think about another idea. And I know in the homework, you may have gotten an answer like this for one of the problems, and maybe you kind of wondered, what the heck is that? That's a big angle. So ponder that. Sometimes people put something like that in their notes. Sometimes they just scribble on their homework. Sometimes they just think. Make sure you're doing one of those things.
Just put it on the bottom of the notes that we did last time.
You're fine. That works.
Here's my work.
Okay. Normally at a time like this, if you were so desired to do so, you could talk about this problem. Feel free to see what people around you think. Again, as you're comfortable, you may do that. All right, and flip her back. I see something on yours again. All right. All right, now, as far as this warm-up answer goes, just for the sake of an answer, it is quadrant 3. Quadrant 3. What I like to do is kind of hold that problem till we take a look at something in a few seconds in the lesson. Now, with the homework, I ended up checking number 60. A lot of times students are curious, so we'll kind of get that figured out. The answer is right around 110 degrees with some change, but pretty close to 110.7-ish. Okay, now, I know there was some concern with the homework. It's going to be normal. I told you guys that you might see some things that are new day to day. And maybe a problem like number 60 is one that can answer some questions. I had some people say, Mr. Naylor, we never did the factor label method. Okay, that doesn't really change too much of what we're trying to do here, because I still want you to know how to convert. And all the factor label method is doing is just helping you to set up basically a ratio that does not need to be turned into a proportion. You don't need to get equal signs and actually make like a proportion, but you're just using a ratio. And the ratio is always 180 degrees to pi, or pi to 180. You can flip it either way. And then what we want to do is we just want to cancel the radians. And the way that you cancel the radians is by putting something in the numerator to do that. And the only thing that you can put in the numerator would be your angle. Your angle is 8 pi over 13. Now listen, if you never did the factor label method, this might be kind of a new idea. That is canceling labels. And the label is radians. And so that label cancels, but the degree label is what we're going to be left with. And so at this point, it's just do the math. The math says that you can divide these pi's away if you'd like to. I think that's smart. And then just multiply 180 times 8/13 on your calculator, I would imagine, and you end up with 110 degrees. Now, number 48B. Number 48B is a common question. Some people asked about it over the weekend. That's fine. I would guess that there's some more of you that are just curious about it right now. If you got it right, you can still kind of watch and just double check, because what we're doing is we're actually taking 144 and turning it back into radians. And this is a little strange because why would you want to turn it back into radians? Honestly, just to show that you understand that process. But most people like to turn things into degrees. And of course, it's already in degrees. But if we want to turn it into radians, we will set up the same ratio, but this time you want to put pi in the numerator. The reason you put pi in the numerator is because you want to keep that label. And so the label that you want to cancel is the degrees. So 144 degrees will cancel literally the degree mark. And what this is saying is that it's no longer in degrees, but rather it's in radians. Again, we don't have a symbol for radians, but we can write that if we want to. Now, this comes out to be 144 pi over 180. By the way, I didn't show you this on Friday. This is something kind of new. And at this point, you've got kind of this big fraction that if you start reducing it, it'll eventually reduce to 4/5. But it's really 4 pi over 5, but you reduce the integers and you get 4/5. Now, another comment about just the homework. I won't say this all year, but it's true that you can check the answers in the back of the book. As I sometimes say, nobody does that because you have to actually flip back there. So you can be the first person, but seriously, bookmark the back of your book and you can check the odd answers. But is there anything else that you want to talk about? Sometimes kids have questions on the even answers, something beyond what I did. Are you sure? Are you guys okay with like the first couple questions? They were kind of different, like 1, 2, 3, 4. Anything that you want to go over? All right. And this is also true all year because remember, this is a little different class. When we're sort of done with the homework, are you done or do you need to go back and do something? You know, it's not something where you just kind of turn the page, now we move on. If you seriously were like, yeah, I didn't really know how to do something, but now I feel a little better, go back and try that problem. Spend a few minutes making sure you're good so the next time you see it, like on a quiz, that you are good. All right, so Quadrant 3. Is there anyone that you wouldn't mind explaining how you thought of this? I didn't really teach this yet. Any way that you got Quadrant 3 and you wouldn't mind explaining a little bit? Brandon.
Well, I just subtracted 360 from 590 since I think that just started me over again. And then I got 230 from that. And then I know like the line in between 3 and 4 is 270. The line between 2 and 3 is 180.
So you feel like you know where 230 is then. Now, the first thing you said is the most intriguing. As you said, I just subtracted 360 because, what was your words again?
It would just bring me back to the beginning of the rotation again.
Okay. Any other ways that you guys thought of it? Similar thing, Julia?
Yeah.
Okay, now, interesting, in fact, not just interesting, but completely correct, but I'd like to still show you where 590 is. I'd like to show you that 590 would actually be in the same place, okay? But it's a different angle. It's a different angle because it has that extra revolution, all right? Just something kind of just process. We're going to do something with that in a second. If you're like, wait a minute, are they the same? They're two different angles, but they're in the same location. Okay, those are both true statements. Now, there's a little bit more that I want to show you when it comes to kind of these introductory ideas. I'm going to call this intro topic 2. I'm not going to lie to you, though, that all of this sort of just blends together. All of these intro ideas. So however you kind of organize it is fine. Most kids will call this number 2 just because I am. And I want to talk to you today about some special angles. I'm just going to kind of generically call it some special angles. And let me give you some quick terminology. It's funny, we've kind of been doing this. I've just not officially said it. when it comes to angles, we're going to have an initial side and we're going to have a terminal side. You're going to find out in 30 seconds that we've kind of already been doing this, but just want to make it official. So we've got the initial side and the terminal side. And the initial side sometimes is called the fixed. That makes sense. Or the starting ray. And honestly, the word initial, I realize that kind of implies that anyway. So we've got the initial side, the fixed or starting ray, and then the terminal side. As you can probably guess, it's the other side, but let's put a word to it. How about the rotating or ending ray? Rotating or ending ray. Now, every angle that we've drawn so far has been this way. We've only had a couple days together, but every angle has been this way. But let me just say something to you now. That's actually the X and Y axis. Very soon, we're going to do something with the X and Y axis, but I want you to actually think of that as the X and Y axis, because when we draw an angle, for example, like this on the X and Y axis, we can make it pretty standard how we're going to describe these two sides, where this will always be the initial side, and then, as it's probably not a big surprise to you, as we rotate it, then we would have the terminal side. So we have the rotation starting on the initial side, and then, of course, ends on the terminal. Now, what I just drew for you isn't that mind-boggling, but it's important because it's standard. It's standard. We actually call it standard position. We call it standard position. Let me define for you standard position, but it's what we've been doing. It's when the initial side is along the positive x-axis. Just process it. It's not supposed to be too tricky, but it's important. It's basically saying that every angle we draw is going to start right here. It's going to start on the positive x-axis. In geometry, you would have had angles just kind of floating in space. You know, I remember seeing them in your textbook. Here's an angle, here's an angle. They never were really positioned in a standard way. Okay, here, the positive x-axis will always be your initial side. Now, a little bit of simple terminology, and now a little bit of a challenge. Maybe, honestly, a little bit more of just something to think about. Now, what should you do, at a time like this? Well, don't wait for me. I'm not going to answer this in 2 seconds. Think about it. Now, some students will think about this by copying this down. That's fine. Some people think about it by just kind of reading it and they're ready to start to do something. Whatever it takes for you to think about it. Now, if you're saying, should I copy it down? Again, I'm being honest. You might not need to. I'm going to give you something like a definition soon. But think, can you do this? And if you're like, well, I want to, Miss Naylor, but I'm not sure, just relax. You might end up drawing something. You might end up writing some numbers. I don't want to say too much because how would you think about this? And again, at a time like this, after you've spent some time thinking about it, if you want to, what did you get? Kind of see, talk, you're allowed to do that. Again, I'm not going to say that every day either, but it's just true. If you want to do that, kind of see what someone else is thinking. Let's do it a little bit more on a big scale then. Anyone think that you have something worth sharing? You're kind of stepping out here. I haven't really told you what this is. You think you have an example? Anna, thank you.
I went with the pair that we did on our warm-up problem.
Okay, so the pair we did on the warm-up problem. Talk to us about it.
So my thought was that because they both end in the same position,
Okay.
they would both have the same terminal side, even though one makes an extra rotation.
Good. Even though they both end in the same position, they would have the same terminal side. I'm sorry, even though one of them has an extra rotation, they still end in the same position, so they have the same terminal side. Okay, now, question for everyone. Are these two different angles right here? Okay, well, maybe you're not sure, because again, this is kind of a new idea, but I want you to realize that the answer is yes. They are different angles. To go to 590 is to do something different. It's quite frankly to spin around an extra time. So these are two different angles. If you're saying, yeah, Miss Naylor, but they're the same. Well, what's the same, as Anna said, is the terminal side. So they're different angles, but they have the same terminal side. Oh, sounds kind of like this statement here. Is there another one that you came up with? I should say another pair. I saw a few people kind of drawing this. Basically what I drew over here. Okay, now, I don't want to take it out of somebody's hands if you drew this.
Yeah, I have it. I just did 120 480.
Okay, so kind of just pretend it's 120 and it's good. So 480, that's 360, and that takes you back to the same place. There's another answer that would match with this one. I'm not sure if I saw somebody do this. I, again, don't want to take it from you if you did. What am I implying here? Well, first off, this angle would have to be negative. Okay, did I spin around an extra time? Not necessarily. I just went a different way. Some negative angle, right? Are you doing like a little thinking about what it would be? I guess it's past negative 180. How far past? Looks like it would take another 60 degrees. We're going to do some of that thinking here in a few days, but just understand that if I go a little bit more, another 60 degrees, you're going to be at negative 240. Now we have a pretty good sampling of examples on the board here for you now to notice something. Okay, definitely want you to notice that these all fit the little statement, but there's something true about all the numbers, like literally the numbers 230 and 590. There's something true about these numbers, even the negative. They all differ by blank. They all differ by you see, it's that extra revolution. It's that 360. Okay, it kind of sounds a little bit like what Brandon was saying back here in the little warm-up. So every one of these numbers is 360 degrees apart. Obviously, it depends on which ones you look at here, but they're all in a multiple of 360. And when numbers are like that, we say that they are coterminal. Coterminal. This would be something you would want to write down, okay, because coterminal angles are essentially what we just discovered. Coterminal angles. It should sound just like the little statement. They are two. I left the word different out of this, but they're two different angles. Maybe you want to squeeze that in there. They're two different angles with the same terminal side. Two different angles with the same terminal side. So two different angles with the same terminal side. Now, remember the little statement or the little idea we were coming up with 360? Let me show you kind of a mathematical definition for getting that idea of like 360 built into this. Okay, same thing. Don't get bogged down first on just copying. I know you're going to want to write it down, but I'd like you to understand what you're writing. It's a little bit more mathematical. First of all, we have this symbol here. This is the theta symbol. Theta is just a Greek letter. We use it as a variable for angles instead of using x. So theta would be like the angle that we have. Now, essentially, we've got an angle. If you add or subtract 360, you're going to get another coterminal angle. That's essentially what this is saying. If you add or subtract 360, you'll be guaranteed to have something that's coterminal. Now, we also have the add or subtract of 2 pi. I hope that doesn't kind of startle you. That just means that you're in radians. But maybe you're wondering what this k thing is. What's k? Okay, it's a common way to describe in mathematics an integer. So in this case, it's kind of like saying I could have one 360. I could have two 360s. We could actually add or subtract multiple 360s. It doesn't have to just be one. Make sure you write down the gist of this. All right, I just wanted you to kind of see the notation, essentially, of theta plus or minus 360k, or theta plus or minus 2 pi k. All right, so we have a pretty straightforward, pretty common question, which is often to find a positive and a negative coterminal angle. A lot of times you'll be asked to find a positive and a negative coterminal angle. And let me give you a couple angles to think about here. How about for like 155 degrees? How about for negative 4 pi over 3 radians? Okay, so to do this, you're just going to real carefully think about the definition of what it means to be coterminal. It's okay if you need to use a calculator or whatever you got to do. I encourage you to do this, but just to make sure that you're on the right track. All you really need to be doing for that first one is probably just adding and subtracting 360. Unless for some reason you wanted to do that multiple times. In other words, you could add or subtract 2 or 3 360s. Most people don't do that, but you could. So you get 515 and negative 205. Honestly, that's it. That's all you really have to do. Now, a little quick trig etiquette. Trig etiquette. There's actually, in Mr. Naylor's mind, something called the math etiquette book. The math etiquette book has all kinds of little statements about when it's the right way to write something, certain things that you shouldn't do. One of the things in the math etiquette book, if you look in the trig chapter, is that if the problem is given in radians, then you want your answer to be in radians. That is, unless, of course, the question is to convert it, like your homework over the weekend. This is in radians. That means I want my answer to be in radians. So use 2 pi. Don't do the problem in degrees. Don't try to do it with 360. Use 2 pi. Make a common denominator with 2 pi. Okay, now basically multiply top and bottom by 3, so we can think of this as 6 pi over 3. But now I can basically add 2 pi, and of course 6 pi and negative 4 pi actually is 2 pi over 3. And then subtract. But you're really subtracting 6 pi. So negative 4 pi subtract 6 pi. Now we're all the way to negative 10 pi. Negative 10 pi over 3. But that's the right way to write that answer, in radians. Go ahead. Where did we take the wrong turn?
Just in the 6 pi. I don't know how I'm confused by that, but I am.
Okay, it's no problem. Even I was just looking at it as I listened to you, I was kind of like, did I do that right? You've got a fraction, but you've got a non-fraction. The only way to put them together is to make them both common, to make them both have the same look. So I need a common d. So now, why am I just putting a 3 down here? Well, I'm not just putting it down there, I'm multiplying it down there. So I multiply the bottom by 3, but then you got to multiply the top by 3. So that's where you see me changing this to a 6, because, again, I multiplied top and bottom by 3. Does that help out? Now, why would you want to do this? Maybe you're kind of like, it sounds good, but why do I want to like spin around an extra time? I already get dizzy just looking at all this. Negative 4 pi over 3, kind of wondering, when you look at that, are you like, what is that? Well, what is that is an angle in a certain location. Guess what? It's in the same location as 2 pi over 3. Now, maybe you're like, but where's that? Well, if you go back to the second day of school, we have a circle, and that number is on that circle. And it's okay to look at it. That's a reference, that circle we made for you guys. So 2 pi over 3 from the circle from last week is about right there. Well, guess what? That's the same place this is. In other words, now we have the ability to understand negative 4 pi over 3. because we know that it's going to stop at the same place. So sometimes these angles, called coterminal angles, can help us to understand something that maybe seems a little bit foreign, like something like a big number like this. Okay. Well, make sure that you made note of the homework, and I'll make note of the different bell schedule. Remember, that homework is always